nature of this talk is very basic. So in this talk, first I introduce about what we meant by the boundary value problem, and then how we may distinguish them as a regularly perturbed problem and singularly perturbed problem. So after this basic introduction about two-point boundary value problem, I will introduce the finite difference method. And then for a test problem, I discuss how we can implement central finite difference scheme and upwind finite difference scheme. Now, to enhance the accuracy of discussed finite difference methods, there are various techniques like Richardson extrapolation, deferred correction techniques. So, among them, I will concentrate myself in this talk to Richardson extrapolation technique, and we'll discuss if solution is known to you, exact solution is known to us, and if exact solution is unknown to us, then how we can verify the numerical order of convergence. So basically there is a formula, so I will discuss the develop how we can develop that formula. Many people use directly that formula. So references is given at the end of this talk. So as you know that while we are solving a ODE of first order, so generally solution of that first order ODE consists a single constant, and while we are solving second order ODE, so solution of second order ODE consists two constants. So based on that, we can say that solution of a given ODE considered as a family of curve. So while we are giving particular value to those constants involving in the solution of the differential equation, we are getting different curves. So if so in this sense, solution of a given ODE is not unique. So to get the unique solution of ODE, if we put some side conditions on the solution and its derivative at specified points, so then the problem under discussion is either said to be boundary value problem or initial value problem. So first question naturally arises, what is the boundary value problem? So as I mentioned over here, a boundary value problem is a differential equation where the side conditions are specified at two or more points of the independent variable. Whereas initial value problem when all conditions are specified at the same point. So generally that point is a starting point in the initial value problem. And in boundary value problem, for ODE, side conditions are typically specified at the end points of the domain. That is, what is the domain for two-point boundary value problem? In one case, a simple closed interval AB. So boundary conditions are specified at the end point A and B for the two-point boundary value problem. So for example, consider this boundary value problem u double prime x plus ux equal to 0 defined over the open interval 0 to pi by 2, and boundary conditions are given u0 equal to 0 and u pi by 2 equal to 0. So this is an example of a boundary value problem. So in general, we can distinguish boundary value problems into two categories. One type of boundary value is said to be regularly perturbed boundary value problem, and another kind of boundary value problem are said to be singularly perturbed boundary value problem. Basically, in this lecture, we will focus only to the regularly perturbed boundary value problem. So, just I am giving idea what we meant by the singularly perturbed boundary value problem and what kind of difficulty we can face while solving the singularly perturbed boundary value problem. Participants, if am I audible to you clearly? Okay. So to define or to distinguish what is the regular perturbation and what is the singular perturbation, consider a simple algebraic equation which is defined by this function p epsilon, which is defined by this problem p epsilon, where this is a uh, uh, algebraic equation x square plus epsilon x minus 1 equal to 0, where what is epsilon? Epsilon is known as a small perturbation parameter, where epsilon it is real and positive, but it may assume very small value and in fact very near to the zero. Epsilon basically approaches to 0. If you solve this algebraic equation, you can see solution to this algebraic equation is this x equal to minus epsilon plus minus square root of epsilon square plus 4 upon 2. So you notice that if you set epsilon equal to 0 in this problem p epsilon, so again your problem remain well posed. You are getting two solutions x equal to plus minus 1. And if epsilon approaches to 0 in this solution in equation 2, again you are getting solution x equal to plus minus 1. That is, solution continuously depend upon the small perturbation parameter epsilon, and there is no change in the solution in both the cases. If you set epsilon equal to 0 in the original problem, again you are getting the solution x equal to plus minus 1. And if you are letting epsilon approaches to 0 in the solution to this algebraic equation, again you are approaching to x equal to plus minus 1. So this is an example of a regular perturbation problem. Now, to show what is the meaning of singular perturbation, so to define, later on I will define theoretically what we meant by regularly perturbed problem and singular perturbed problem. So consider this example for the singular perturbation. Here epsilon is multiplied by the lower order term. So instead of this, let epsilon is multiplied by the higher order term, that is epsilon is multiplied by with x square. So consider this algebraic equation epsilon x square plus x minus 1 equal to 0. So here, which is defined by the function fx epsilon. So again you can easily find out the root of this algebraic equation, which is given by this equation number 4, x equal to minus 1 plus minus square root of 1 plus 4 epsilon upon 2 epsilon. So again notice that if you set epsilon equal to 0 in this equation number 3 in algebraic equation, so resulting problem you can denote by p naught. And here you can notice that if this problem P naught has only a single solution, which is x equal to 1. And while you are letting epsilon approaches to 0 in equation number 4, equation number 4 gives the root of this algebraic equation. So you can see x approaches to, which is the solution, x approaches to 1 and minus infinity. So you can notice that P epsilon here, you can notice that P epsilon here is not approaches to P0 as epsilon approaches to 0, where, so that's why it is said to be singularly perturbed problem. So we can define regularly perturbed problem and singularly perturbed problem in this way. Suppose you are having a problem P epsilon, which is described through a equation fx epsilon 0. Then this problem is said to be regularly perturbed if x epsilon, what is f x epsilon? X epsilon is the solution to this problem fx epsilon epsilon equal to 0. So if x epsilon approaches to x naught as epsilon approaches to 0, where x naught is defined as a solution to the problem p naught, that is to the solution of fx naught equal to 0. So in that case, problem is said to be regularly perturbed. But if x epsilon is not approaching to x naught as epsilon approaches to 0, then the problem p epsilon is called singularly perturbed. Thus, a perturbation problem P epsilon is regular if its solution x epsilon show smooth dependence on the small parameter epsilon. So, this definition is clear to you, audience? Any doubt? So, I will give example about the singularly perturbed boundary value problem and regularly perturbed boundary value problem. No. Okay. So, let me 1 minute. So, as I said, suppose you are having a problem P epsilon, which is defined by the f x epsilon epsilon equal to 0. What is the corresponding problem P naught? P naught is equal to f x naught, 0 equal P x naught. P naught is a problem which is defined by this equation f x naught 0 equal to 0. So note that problem P epsilon is said to be regularly perturbed if x epsilon approaches to x naught as epsilon approaches to 0, where x naught is the solution to the problem P naught. And if you don't have smooth dependence on a small parameter epsilon for the solution x epsilon, then that problem is said to be singularly perturbed. So that differentiation between regularly perturbed and singularly perturbed will be clear in these two examples. Here, consider two different boundary value problem, which is defined by the equation number 5 and equation number 6. So, in equation number 5, a small parameter epsilon is multiplied with the lower order term, that is with ux. So, this problem is in this problem that problem is defined by minus u double prime x plus epsilon ux equal to fx, and domain of the problem is the open interval 0 1, and boundary conditions are specified u0 equal to u1 equal to 0, while another problem is defined in equation number 6, where perturbation parameter epsilon is multiplied with the higher order differential term, that is with u double prime. So you can notice that if you set epsilon equal to 0 in equation number 5, if you set epsilon equal to 0, nothing remarkable happen, because in that case equation number 5 reduced to minus u double prime equal to fx. So again this equation remain well posed OD. But if you and in fact you can get a solution to this minus u double prime equal to fx, you can easily solve it, and with the specification of boundary conditions you can get the value of the constant c1 and c2. But if you set epsilon equal to 0 in equation number 6, then problem reduced to ux equal to fx, and that problem is ill posed unless f0 equal to f1 equal to 0, because if solution if epsilon equal to 0, so that equation number 6 reduced to ux equal to fx, and boundary condition are u0 equal to u1 equal to 0. So boundary condition only satisfied when the function value f is equal to 0 at the point x equal to 0 and x equal to 1. So we cannot satisfy u equal to f and the boundary conditions. Okay. So what happened if epsilon approaches to 0 in the singularly perturbed problem? So in that case, boundary layer appears in the solution. So boundary layer, that term borrowed from the physics, And while you apply classical numerical methods to solve singularly perturbed problem, so basically unacceptable large oscillations occurs if you apply classical numerical methods on uniform mesh. So to tackle singularly perturbed problem, you need to construct layer adopted meshes, and on that you need to apply the numerical methods. So in general, it's very difficult to tackle the singularly perturbed problem, and it is a very active area of research nowadays. But in this lecture, I am focused only to the 2 point regularly perturbed boundary value problem. So let in on some other occasion, I will discuss about the singularly perturbed problem. So it is well known that a general form of second order boundary value problem is given in this equation, where the second order boundary value problem is defined by the operator L, where and boundary conditions are specified by the function B. Note that given boundary value problem is linear if both the function f and boundary conditions are linear, and if function f and this function b, or if either f or b or both are non-linear, then boundary value problem is said to be non-linear. So this is the basically difference between the linear boundary value problem and non-linear boundary value problem. So a general second order linear ODE can be written in this form: a2x u double prime x plus a1x u prime x plus a naught x ux equal to fx. So if a2x is not equal to 0, so one can normalize this equation by dividing all terms by a2x to get this general form of second order linear ODE: u double prime x plus px u prime x plus qx ux equal to rx, where p is known as the convection coefficient, q is a reaction coefficient, and r is the reaction term in this equation. And in fact, it is a one-day linear elliptic equation. And if this equation number 7 considered among one of these well-known boundary conditions, which is known as, I think all of you are aware with the Dirichlet boundary conditions, Newman or natural boundary conditions, Robin or mixed boundary conditions. So then that equation along with one of the above boundary condition is said to be second order, general form of a second order linear boundary value problem. So in Dirichlet boundary conditions are easy to tackle. In Dirichlet boundary condition, we assign the value of the solution at the end point. And in natural boundary conditions, value of the derivative is specified at the end point of the interval. And in mixed boundary conditions, a linear combination of solution value and its derivative are specified at the end point. So there a large number of applications of second order boundary value problem in diverse field of science and engineering. For example, second order boundary value problem are used to model the behavior of vibrating structures, including springs, beams, and plates. And these problems help determine frequencies, modes, and damping characteristic of the uh, vibrating structure. Also, second order boundary value problem are used to model the distribution of stress and strain within material, especially in situation involving static or dynamic load. In electrical engineering, these boundary value problem used to model the behavior of circuit, also used to analyze the behavior of transmission line. In physics, these boundary value problems are used to model the distribution of heat in solid objects or fluids, considering factors like temperature, conductivity, and convection. Also, second order boundary value problems are used to model electromagnetic field. In biology, population dynamics modeled by second order boundary value problem. In fluid dynamics, second order boundary value problem often happen to analyze fluid flow in pipes, channel, and other geometries, considering factors like pressure, velocity, and temperature. So, in a nutshell, you can find a large number of applications of second order boundary value problem in real world problems. Now, main question is that why we need numerical methods to solve second order boundary value problem. So it is well known that if a given differential operator is linear with constant coefficient, in that case it is easy to solve to that differential operator by finding the auxiliary equation. And in fact, if you are having variable coefficient, in some cases you are still able to solve, like Cauchy-Euler equation. And if coefficient function p and q are analytic, in that case, power series solution exists there. And still, if coefficient function p and q are fails to be analytic, in that case, in some cases, series solution also exists, which is known as Frobenius series solution. But these are very limited type of equations which are solvable analytically. So, if those problems which do not involve constant coefficient, and in fact, right hand side term, that source term is complex, is represented by some complex functions, and if second order boundary value problem involves some nonlinear terms, or boundary condition itself are represented by some difficult functions, in that case, still you can't find a closed form analytical solution. So in that case, we don't have any choice rather than to solve those boundary value problem with numerical methods. So numerical methods like finite difference method, finite element method, shooting method, and other methods provide a systematic way to approximate solution with a reasonable level of accuracy, and these methods can be implemented on computer for efficient calculations. In this method, first we discretize the domain, and then derivative term are replaced by some algebraic equation. In case of finite difference method, derivative term are replaced by the difference formulas, and ultimately, either if you are using FDM or finite element method or collocation method, ultimately all these method leads to a system of linear or non-linear equations which you can solve easily by using any numerical methods. So with appropriate choice of method and discretization, numerical methods can provide accurate solution, especially when the problem has a smooth solution. So in this slide, just I am giving a brief overview of various numerical methods. So in finite difference method, core idea is to replace the derivative with algebraic approximations on discrete grid, and ultimately that differential operator transform to a system of linear equations with the application of finite difference method, and that system of linear algebraic equations you can solve numerically by using any numerical method. So the main advantage of finite difference method is that it has a very simple structure and very easy to implement, and it allow easy development for higher order accurate scheme, which can lead to more precise solution. In collocation method, we assume a particular form of the solution. It may be a polynomial function, it may be in the form of trigonometric functions, it may be in the form of exponential functions, and then enforce that solution to satisfy the differential equation and boundary condition at specific collocation points. So in collocation methods, again, at the end, we lead to a system of linear or non-linear equations depending upon the problem under discussion is linear or non-linear. In finite element method, we divide the domain into some smaller elements and approximate the solution using basis function within each element. Finite element method, application of finite element method to a second order boundary value problem again lead to a system of linear equations. So advantage of FEM over the FDM is that if you have a complex geometry of the domain, our boundary conditions are specified by some difficult function. In that case, FEM work excellent works very well over the finite difference method. But discussion over the finite element method is beyond the scope of this lecture. So I will concentrate myself in this lecture over the finite difference method only. Dear participants, any query from your side? Okay. So to give an idea of the construction of the finite difference scheme, we consider this simple second order boundary value problem with Dirichlet boundary conditions, which is defined in the equation number 8. So differential equation is differential operator is given by L, where coefficient function P and Q we are assumed sufficiently smooth, and also we assume that coefficient function Px is bounded below by a constant alpha which is greater than 0 and Qx is less than equal to 0. Later on, I will discuss why I am imposing these conditions on the coefficient function P and Q. Because of these conditions on coefficient functions P and Q ensure the existence of a unique smooth solution. Although theoretically we can found that with the help of a discrete continuous minimum principle and stability estimate, there exists a unique solution, analytical solution to this boundary value problem. And to ensure this, we required these restrictions on the coefficient function. And while I developed the finite difference method like central finite difference scheme and affine finite difference scheme, there I also will discuss these conditions also required for the stability of the finite difference scheme. So that's why I impose these conditions on the coefficient functions over here. So first, we show that the boundary value problem defined in equation number 8 satisfy this continuous minimum principle. So statement of continuous minimum principle is that suppose u is a function belongs to C to omega bar. Omega bar in our case is the domain open close interval 0 to 1, which satisfy u a is greater than equal to 0, u b greater than equal to 0. That is, we assume that boundary conditions are non-negative and operator L satisfy this condition L ux less than equal to 0 for all x belongs to omega, then ux greater than equal to 0 for all x belongs to omega. Basically, continuous minimum principle show that our continuous operator L here is inverse monotone. Inverse monotone means that, and since problem under discussion is linear, so it ensures that there exists a unique solution to this continuous problem. So proof of this continuous minimum principle is simple. We prove it by a contradiction. Here we assume that there exists a point t belongs to omega bar for which ut is the minimum of ux over the domain omega bar, and we assume that ut is less than 0. That is, function value of u, basically u is here the solution of the given boundary value problem, at the point t is negative. Therefore, from the given boundary conditions, we assume that in this statement ua greater than equal to 0, ub greater than equal to 0. So that implies if ut less than 0, then this point t cannot be a boundary point. So it follows from the definition of t, because t is the point of minima of ux over the domain omega bar. So what does it imply? At the point t, u prime t is equal to 0, and u double prime t is greater than equal to 0 by the first order and second order derivative test for the point of minima. So, but then at the point t, u double prime t, that is a positive term because t is the point of minima. This is pt. U prime t is equal to 0. Qt we already, this is t. Qt we already taken is less than 0, and ut is also we have taken less than 0. So qt and ut both are negative, so qt into ut both will product of them will be positive. So that implies at the point t, operator l take the positive value greater than equal to 0, which is a contradiction because of lux is less than equal to 0 for all x belongs to omega, and t is an interior point of the domain. So it follows that our initial assumption, this assumption is wrong. It follows that ut greater than equal to 0, and where t is the point of minima. So that implies ux is always positive for all x belongs to omega bar. So this continuous comparison principle ensures that the operator L here discussed in continuous problem is inverse monotone. An immediate consequence of this continuous comparison principle is the following stability estimate for the solution U. So if Ux is the solution of the boundary value problem, then solution U satisfy this stability estimate that is bounded by this. So this stability estimate we obtain by constructing the barrier function phi x, which is defined over here, norm of r upon alpha plus maximum of mod a mod b. Mod a and mod b are the boundary conditions. Alpha is the lower bound for the convection coefficient, and norm r is the source term. So we construct this barrier function and we apply this continuous minimum principle to this barrier functions to obtain this stability estimate. Since problem under discussion is linear, so it ensures that continuous problem itself has a unique solution. And this is under the assumption on these coefficients px greater than equal to alpha greater than 0, qx less than equal to 0. Later on, we will show that central difference scheme and upwind difference scheme again stable under these conditions on the coefficient functions. If these conditions are not satisfied, central finite difference scheme and upwind finite difference scheme will not be stable. Now, to develop a finite difference scheme for the given problem, first we discretize the domain omega bar into an uniform subinterval with uniform mesh width, which is defined by h equal to b minus a upon n. Note that it is not essential to take uniform subintervals. And in fact, if we consider singular Putter boundary value problem, you can't solve singular Putter boundary value problem on the uniform mesh, because in that case if you apply classical finite element method or classical upwind finite difference scheme on uniform mesh to solve singular Putter problems, you will get spurious oscillations in the numerical solution. because of for singular problems, as epsilon approaches to zero, boundary layer appears. So to resolve boundary layers, you need to construct layer adopted masses which are generally non-uniform. Okay, but here this is a very simple case. Uh, so that's why here we discuss only the uniform mass. So with this mass spacing, into mass points are you can find with this xi equal to a plus ih correspond to I equal to 0, xi equal to a correspond to I equal to 1, x1 equal to a plus h. What is a equal to x naught, and so on. And finally xn equal to a plus nh. Nh is equal to uh, nh equal to b minus a, that is xn will be equal to b. So now first we construct finite difference formula to approximate the derivative term. So while we are solving boundary value problem by finite differences, we replaced all derivative terms by corresponding finite difference approximation. So to construct finite difference approximation of derivative term, we consider a Taylor series expansion for the solution ux in this way. If solution ux is sufficiently smooth, for example, if in this case we assume that solution u is k times continuously differentiable, then you may have this kind of Taylor series expansion for the solution u. Ux equal to uxi plus x minus xi u prime xi plus square of x minus xi upon 2 factorial u double prime xi and so on, x minus xi to the power k factorial into kth derivative of u at some point xi, where xi is some point lie in between xi and x, and this term is known as the remainder term of the Taylor series expansion. So if we replace this point x by xi plus 1, that is xi plus h, in that case uxi plus 1 is equal to uxi plus h u prime xi plus h square by factorial to u double prime xi plus h cube upon 6 triple prime xi and so on h to the power k upon k factorial, kth derivative of u at the point xi I plus 1. Basically, the point x we replaced by xi plus 1, where xi plus 1 is nothing, that is equal to xi plus h. So x minus xi, that is xi plus 1 minus xi, will be equal to h. Similarly, if we select x equal to xi minus 1 is equal to xi minus h, so it gives us this Taylor series expansion of uxi minus 1. This is uxi in subscript minus 1 is equal to this one. Now to get approximation of first order derivative, if we set k equal to 2 in equation number 10 and solve it for u prime xi, so we will get this thing, u prime xi is equal to uxi plus 1 minus uxi upon h minus h by 2 u double prime xi I plus 1, where xi I plus 1 is a point which lie in between xi and xi plus 1. Okay, so this formula is the approximation of first order derivative at the point xi, and it is approximated by ui plus 1 minus ui upon h, and this approximation we obtained from this by equation number 10, setting k equal to 2 and then solving for u prime xi. So this formula is known as forward finite difference approximation of u prime xi, and that term minus h by 2 u prime u double prime xi I plus 1. This is the error. This term is known as the error in the approximation, and it is defined as the local discretization error tau I. So one can notice that this approximation is accurate of order of h, because truncation error term is of order of h. Similarly, setting k equal to 2 in equation number 11 and then solving u prime xi, we will get this approximation of first order derivative, which is given in this, and this approximation is known as backward finite difference approximation of u prime xi. Again here, this approximation is first order accurate. Now if we subtract equation number 11 from equation number 10 and set k equal to 3, so we will get this central difference approximation for the first order derivative. U prime xi is approximated by this formula, ui plus 1 minus ui minus 1 upon 2h, where truncation error is given by this term minus h square by 6 u triple prime xi I. So you can notice that this approximation is, sorry, second order accurate. But here you require different kind of regularity for this finite difference approximation. If although this forward finite difference approximation and backward finite difference approximation is accurate of first order, but they require less regularity on the continuous solution. While if you approximate first order derivative by central difference approximation, you are giving higher accuracy, but it required higher regularity on the continuous solution. That is, solution at least should be third times continuously differentiable. Okay. And also one thing you can notice that higher order accuracy of central finite difference approximation you can get only on the uniform mass. If your mass is non-uniform, then central difference approximation also will be first order accurate, because in that case, while you are subtracting equation number 11 equation number 11 from equation number 10 by setting k equal to 3, that second order term will not be cancelled out on the non-uniform mass, because in that case, for example, let me precise, suppose this is the point xi minus 1, this is xi, and this is xi plus 1. In between xi minus 1 and xi, mass width is h1, and in between xi to xi plus 2, 1, mass width is h2. So uxi plus 1 in equation number 10 will be equal to uxi plus h1 u prime xi plus h1 square, because so xi to xi plus 1, mass width is h2, sorry. Uxi plus 1 will be equal to uxi plus h2 u prime xi plus h2 square upon factorial to u double prime xi plus h3 square to the power 3 upon 6 u triple prime xi, and so on, h to the power k upon k factorial. While on the interval xi minus 1 to xi, mass width is h1 if mass is non-uniform. In that case, uxi minus 1 will be equal to uxi minus h1 u prime xi plus h1 square upon 2 u double prime xi minus h1 to the power 3 upon 6 u triple prime xi, and so on, minus h1 to the power k factorial into uk xi I minus 1. So while you are setting k equal to 3 and subtracting equation number 11 to 10, that term will not be cancelled. This term will not be cancelled out because of mass is non-uniform. So in that case, you are getting only first order accuracy in the central difference approximation of first order derivative term. But while mass is uniform, in that case, h1 equal to h2, and this term will be cancelled out. So note that central difference approximation provide higher accuracy only on the uniform mass, not on the non-uniform mass. Is it clear? Any doubt? Okay. So in the same manner, adding equation number 10 and equation number 11 with k equal to 4, we can get the second order finite difference approximation for the second order derivative term. Second order finite difference approximation, why? Because of the here this for this approximation truncation error is again of order of h square. So this is the central difference approximation for the second order derivative term. And also note that in the same manner, we can find out the approximation for the higher order derivative terms by using Taylor series with with the inclusion of more points. That is, more points means that you need to find out the Taylor series at the point xi minus 2, xi plus 2, if you are interested to find out the finite difference approximation of the third order derivative at some point xi and so on. But here we are considering only second order 2-point boundary value problem. So it suffices for us to get the approximation of derivative term up to second order finite difference approximation. So first I will discuss central finite difference scheme for the problem under discussion, which is defined in equation number 8. Now to solve boundary value problem, we construct a central finite difference scheme by replacing the first order derivative term and second order derivative term by their central finite difference approximation. So in that case, central finite difference scheme will take this form, which is given in equation number 12. So analogously, that continuous operator L, discrete operator, we use this notation LCN for the discrete finite difference operator. So LCN is equivalent to ui plus 1 minus 2 ui plus ui minus 1 upon h square. What is this? This is the central difference approximation of the u double prime plus pi ui plus 1 minus ui minus 1 upon 2h. What is this? This is the approximation of u prime x at the point xi plus qi ui equal to ri. Ui means value of solution u at the point xi, and boundary conditions of course specified by u0 equal to a and un equal to b. Because what is u0? U0 means function value of u at the point A, and un function value of u at the point B. So after simplifying this equation number 12, we get a system of n plus 1 linear algebraic equations into the n plus 1 unknowns. Unknowns are u0, u1, un. So u0 and un we know by the boundary conditions, and and in interior equations reduce to this bi ui minus 1 plus ai ui plus ci ui plus 1 equal to h square r1, where bi is nothing. Bi is the coefficient of ui minus 1. So you can notice in equation number 12 what is the coefficient of ui minus 1. 1 upon h square. H square we have taken on the right hand side. So 1 minus h by 2. This is the coefficient of ui minus 1 in the equation number 12. AI is equal to minus 2 plus h square qi, and ci is equal to 1 plus h by 2 pi. So here note that we have taken pi is greater than 0. Am I right? So in that case, and since h is positive, ci is positive. We have taken qi is negative. So minus 2 h square is positive. So minus 2 plus h square qi, that is ai term, is negative. And for sufficiently small value of h, because central difference approximation have restriction on the mesh width h for the stability, and that is due to this term. Later on I will discuss in detail. So for sufficiently small h, bi is also positive. Now there are two ways to solve this system of n plus 1 linear equations in n plus 1 unknowns. Either you can solve it directly, or you can use boundary conditions to reduce it to a system of n minus 1 linear algebraic equations in n minus 1 unknowns. In that case, unknown will be u1, u2, and un minus 1, because u0 and un you know by the boundary conditions. So there are two ways. Either you consider boundary conditions together in this way and consider the system of n plus 1 linear equations with n plus 1 unknown, or use these boundary conditions to eliminate the term u naught and u1 from the equation correspond to I equal to 1 and I equal to n minus 1 in this. So here, since boundary conditions are simple, so here we will opt second way to eliminate the term u0 and un. So now using boundary condition to eliminate u0 and un from b1 u0 plus a1 u1 plus c1 u2 equal to h square r1. Note that this equation is correspond to I equal to 1 here, and bn minus 1 un minus 1 plus an minus 1 un minus 1 plus cn minus 1 un equal to h square rn minus 1. This equation here is correspond to n minus 1. So we find a1 u1 plus c1 u1 is equal to h square r1 minus b1 u naught, but u naught is equal to a, so you can get this equation. And bn minus 1 un minus 1 plus an minus 1 un minus 1 is equal to h square rn minus 1 minus cn minus 1 un is equal to b, so you can get this equation correspond to I equal to n minus 1. So all other equations correspond to I equal to 2 to n minus 2 will remain the same, whatever is given in this equation number 13. So just equation correspond to I equal to 1 and I equal to n minus 1 will transform to another equations with the help of these boundary conditions. So in this way, we can get a system of n minus 1 linear equations with n minus 1 unknown. Unknown are u1, u2, un minus 1. And that system of n minus 1 linear equations can be written in matrix form in this way: a u equal to f, where matrix A is this tridiagonal matrix. All other entries are 0 in this matrix. So on the diagonal, we have entries AI. On the upper subdiagonal, we have entries CI. And on the lower subdiagonal, we have entries BI. Unknown vector is this u equal to u1, u2, un minus 2, un minus 1. This is the unknown vector, and right hand side vector f is equal to h square r1 minus b1a, second h square r1, and so on h square rn minus 2, and h square rn minus 1 minus cn minus 1b. So here this first term and last term in this right hand side vector is changed because of the use of boundary conditions, and so that's why equation I equal to 1 and n minus 1 transform to this one. Now, our ultimate aim is to discuss the solvability of this system of equations AU equal to F. We know that that system is solvable if A is non-singular matrix. Am I right? So we will check this tridiagonal matrix whether it is non-singular or not. So if that matrix A is non-singular, then unknown vector you can get by this U equal to A inverse F. So as you get the unknown vector, so you can get the solution vector U. Okay. So here we ensure that that system AU equal to F will be solvable, or this system of linear equation is stable if coefficient functions Qx is less than 0 throughout the domain. That is, at the mesh points Qi is less than 0 and Pi is positive. So we will show that thing. So for numerical stability and convergence for the unique numerical solution, we often aim for diagonal dominance. So we ensure that matrix A is non-singular with the help of concept of diagonal dominancy of the matrix A. We know that matrix A is diagonally dominant because this is a tridiagonal system. So matrix A is diagonally dominant if mod AI is greater than equal to mod of BI plus CI. Is it clear? Yes, Satyendra, what is your query? Which slide you have doubt? Okay. So here diagonal entries are given by this term minus 2 plus h square qi. Upper subdiagonal entries are given by bi, that is 1 minus h by 2 pi, and lower subdiagonal entries are given by this 1 plus h by 2 pi. Okay. So this is the general condition for the diagonal dominance for the given system of linear equations for the given matrix A. Now, to simplify this general condition for the diagonal dominance for the matrix A, we need to consider the sign pattern of the coefficients Pi and Qi and those which lie in these absolute values. So first we assume that h is small enough so that 1 minus h by 2 mod Pi is greater than 0. And minus 2 plus h square qi is less than 0. If minus 2 plus h square qi is less than 0, so in that case absolute value of this mode of minus 2 plus h square qi will be equal to minus 2 plus h square qi. Okay, so note that if qi is less than equal to 0, if qi is less than equal to 0, then of course minus 2 plus h square qi definitely will be 0 because minus 2 is a negative term, h square is positive. If qi is less than equal to 0, then whole minus. So here this condition qi less than equal to 2h square that required to be minus 2 plus h square qi is less than 0. Now if this condition we involve with diagonal dominance condition, then common conditions will come qi less than 0, which I am showing in the next slide. Note that if pi can be positive or negative, then the absolute value on the right hand side, what is the right hand side? Right hand side, this side. sum of bi plus ci, then it is very crucial. So first we consider the right hand side sum, mod of 1 minus h by 2 pi plus mod of 1 plus h by 2 pi. So using triangle inequality, mod of L plus mod of M is greater than equal to mod L plus M, or more precisely, we can use that inequality, that equality, mod of x minus y plus mod of x plus y is equal to twice of maximum of mod of x mod of y, with x equal to 1 and y equal to h by 2 pi. So this sum will be equal to 2. This sum will be equal to 2 if h by 2 mod pi is less than 1, that is mod pi into h less than equal to 2, or h is less than equal to 2 upon mod pi. So and this is generally true for very small h. So with this diagonal dominance condition becomes, so if that right hand side sum is 2, and that sum is 2 when mod pi into h by 2 is less than 1, then this diagonally dominance condition becomes mod of minus 2 plus h square qi is greater than equal to 2. Now that implies two possibilities. One possibility is that minus 2 plus h square qi is positive. One possibility is that minus 2 plus h square qi is less than 0. Am I right? Okay, sorry, is greater than equal to 2. So if minus 2 plus, sorry, there are these two possibilities we have. If minus 2 plus h square qi is greater than equal to 2, that implies qi is greater than equal to 4 upon h square. So h is the mass width, that is very small. So what does it imply? Qi should be very large and positive, which is very unpractical restrictions on the coefficient function Qi. So another possibility is that minus 2 plus h square qi is less than 0. So in that case, absolute value of this will be minus 2 plus h square qi, and in that case absolute value should be greater than equal to 2. So while we are simplifying it, it implies that qi less than equal to 0. But here in the previous slide we discussed that minus 2 plus h square qi less than 0 if qi less than 2 upon h square. This is the condition alone, this term minus 2 plus h square qi less than 0. But while we accumulate this condition with the diagonal dominance condition, so a common conditions come out which is qi less than 0. So qi less than upon 2h square, that comes only from this one, and this qi less than equal to 0 come accumulating this condition with diagonal dominance condition. So thus a common practical sufficient condition, assuming that h is small enough such that h by 2 mod pi less than 1 and qi less than 2 upon h square, so that diagonal terms ai equal to minus 2 plus h square qi is negative, is qi less than equal to 0. Hence, diagonal dominance require this condition and this condition, or this condition. But I already discussed that qi greater than equal to 4 upon h square. That is very unpractical conditions on the coefficient function qi, because in that case qi should be very large, because h is very small and h square will be more small, and so that qi will be very large quantity. Okay, so just we have these restrictions, and we already taken that pi is positive, so h by 2 pi should be less than 1. So in that case mass width h should be very small, so that is the restriction for the stability for the matrix A. So if mass width h is very small while you are solving a given 2-point boundary value problem with the central difference scheme, in that case you can get a stable system. And this condition also we required qi less than 0. So with this assumption on the coefficients pi and qi, the system matrix A is strictly diagonally dominant, and if it is strictly diagonally dominant it will be non-singular, and if A is non-singular we can solve the system AU equal to F for unknown vector u, for unknown terms u1 u2 un minus 1 to get a unique solution vector u. So this discussion, yes, Satyendra. So is there any doubt why? Because here, while I discussing the stability for this matrix A, I have not taken the conditions in on coefficient function pi and qi. Just I am simplifying them by using the diagonal dominance condition, and ultimately come out that qi should be less than 0 and mass width h should be less than equal to 2 upon mod pi. So that's why I have taken initially pi is positive and qi is negative. So any doubt? Participants, any query from your side? Okay. So far, I have discussed that system AU equal to F is solvable under the condition that QI should be less than equal to 0 and H by 2 mod PI should be less than 1. Now, let me define the local discretization error. So, local discretization error, we need to show that given approximation is consistent, derived is consistent or inconsistent. So we define local discretization error in this way. Suppose we have an OD of the form MUX equal to 0 and MHU be the difference approximation of it, with M and MH being differential and difference operator. M here represent the differential operator and MH represent the difference operator. Then the local discretization error or the local truncation error at xi is defined by this. Tau I is equal to MH UXI. So to find the local discretization error for the constructed central difference scheme for the given boundary value problem, we consider differential operator M in this way. MUX is equivalent to 0, that is MU will be equivalent to U double prime plus PX U prime X plus QX UX minus RX equal to 0. And corresponding finite difference approximation MH will be in this form. That is that right hand side we have taken on left hand side, uxi plus 1 minus 2 uxi plus uxi minus 1 upon h square plus pxi uxi plus 1 minus uxi minus 1 upon 2h plus qxi uxi minus rxi. Now using the central difference formula for the first and second derivative and corresponding truncation error term which I discussed, and with the definition truncation error term will be equal to, because uxi plus 1 minus 2 uxi plus uxi minus 1 upon h square, that is equal to u double prime xi plus h square by 12 u for xi I. In the same manner, uxi plus 1 minus uxi minus 1 upon 2h, that is equal to u prime xi plus h square by 6 u triple prime eta I. where xi and eta I lie in between xi minus 1 and xi plus 1. So using that thing, truncation error is defined by this. But you know that u double prime xi plus p xi u prime xi plus q xi u xi minus r xi is equal to 0. So using that differential equation, truncation error reduced to this. Truncation error term is given by h square by 12 u for xi I plus pxi h square 6 u triple prime eta I, where xi I and eta I lie in between xi minus 1 and xi plus 1. And also note that this truncation error term also reveal that we required at least fourth order regularity on the continuous solution. Solution U should be at least 4 times continuously differentiable. Okay. So that truncation error term also show that we expected our approximation is second order accurate. We might have accepted the local discretization of the central difference approximation for the boundary value problem is of order of h square. Now, let me define the consistency, what we mean by the consistency of a finite difference scheme. The difference scheme MHUI equal to 0 is said to be consistent with the continuous problem MU equal to 0 if truncation error term approaches to 0 as H approaches to 0. That is, if we are getting mass getting refined, finer and finer, then it means that difference operator approaches to the differential operator. That is, difference operator is consistent with the differential operator as h approaches to 0. So here, for the constructed central finite difference scheme, we find that truncation error term is this, and one can easily notice that truncation error term approaches to 0 as h approaches to 0. So what does it mean? It means that constructed central finite difference scheme is consistent with the given differential equation which define the boundary value problem. Now, a finite difference scheme is said to be stable if the numerical solution depends continuously on the input data. What are the input data? Input data may be the right hand side function, may be the boundary condition. So, if constructed finite difference scheme, then constructed finite difference scheme is said to be stable if numerical solution continuously depends on the input data. That is correspond to, in a rough sense, if we say that if correspond to a small change in the input data, we have only small changes in the output data. Output data, what is over here is the solution. That is, you can think it as a black box problem. So you are having some changes in the input data. So correspond to that, if there is a small changes in the output data, so that system is stable. If correspond to a small change in input data, there is a large changes in the output data, then system is unstable. So in that sense, a finite difference scheme is stable if the numerical solution depends continuously on the input data. If it is doesn't depend on the continuously on the input data, then there may be a large variation in the solution correspond to the small perturbation in the input data. So we can define stability of finite difference scheme in this way. A difference scheme MHUI equal to 0 is said to be stable if there exists a constant c greater than 0 such that norm of the solution vector u is bounded by this term. Mod u 0, that is a boundary condition on the left boundary. Mod un is the right boundary, and norm r is the norm of the right hand side vector. because if your equation is u double prime x plus px u prime x plus qx ux equal to rx. So this is the norm on the right hand side vector as h approaches to 0. In other words, the scheme is stable if norm u is less than equal to c norm f. So that condition comes from the corresponding system of linear equations a u equal to f. So if a is non-singular and a inverse exists and A inverse is bounded by some positive constant C, then you can say that your scheme is stable and you will get this condition. And here this constant C should be independent of mesh size. It should not be depend upon the mesh size. So above definition of stability, which I discussed over here, translate to the following condition on the coefficient matrix A. Matrix A should be non-singular. Matrix A should be diagonally dominant as discussed earlier, or one another you may say that if matrix A should be monotone, inverse monotone, that is matrix A should satisfy M matrix criterion. If matrix A satisfy M matrix criterion, then it is suffice to show the stability of the constructed finite difference scheme. Then in that case, diagonal dominance doesn't require. In that case, if matrix A is irreducible diagonally dominant and of diagonal entries are positive, so of diagonal entries are positive, then you can say that matrix A is a matrix A is a M matrix. So now question is that what we meant by the M matrix. So M matrices are the discrete counterpart for the inverse monotone differential operator. For the continuous operator, we satisfy that differential operator L satisfy the continuous minimum principle or continuous maximum principle or continuous comparison principle. So if continuous operator L satisfy the continuous comparison principle, we say that continuous operator is inverse monotone. So so the discrete counterpart of it is the discrete comparison principle. So a discrete scheme of finite difference scheme is satisfy discrete minimum principle or discrete maximum principle, or in other words satisfy discrete comparison principle if associated matrix A is either M matrix or negative of a M matrix. So here matrix A is said to be L naught matrix if of diagonal entries are less than equal to 0. And matrix A is said to be inverse monotone if for any two vector VW belongs to Rn, AV less than equal to AW, which implies V less than equal to W. It means that it means that matrix A is inverse monotone if A inverse exists and A inverse is positive. In that case, matrix A is said to be inverse monotone. So to be inverse monotone for a matrix, for a square matrix, A inverse should be exist and A inverse should be positive. Now a matrix A is said to be M matrix if it is L naught matrix and is inverse monotone matrix. So in other words, a matrix A is an M matrix if all of diagonal entries are less than equal to 0 and inverse for that matrix exists and with A inverse less than equal to 0. So there is one another criteria to be checked whether given matrix is a matrix or not. So that depends upon the sign pattern and it is simple for the tridiagonal matrix. If for a tridiagonal matrix of diagonal entries are positive and of diagonal entries are less than equal to 0 and matrix tridiagonal matrix is irreducible diagonally dominant. Irreducible diagonally dominant means that diagonal entries AI should be greater than BI plus CI irrespective of their uh, absolute value. So in our case, for central finite difference scheme, matrix A is the negative of n matrix provided Qi is less than equal to 0 and H less than 2 upon mod Pi. As the element of the coefficient matrix satisfy the following sign pattern. AI is less than 0, AI is the diagonal entries, BI is positive, CI is positive, and BI plus AI plus CI is less than 0. So that is for the given matrix A. So if you consider matrix minus A, for matrix minus A, AI is greater than 0, BI will be less than 0, and CI will be less than 0, and BI plus AI plus CI will be greater than 0. That is matrix minus A is irreducible, is irreducible diagonally dominant. So that's why in our case matrix A is the negative of NM matrix. So, thus, as discussed above, stability in in this context means that inverse of the matrix A is bounded by some positive constant independent of H, such that norm A inverse is bounded by C. So, it ensures the stability of the constructed finite difference scheme. So, and that stability is ensured under the condition Qi less than 0 and H less than by 2 upon mod Pi. Note that this condition h less than 2 upon mod pi is known as the Piclet number condition, which ensures that convection term pi doesn't dominate the diffusion term. If convection term dominate the diffusion term, then then uses of standard centered finite difference of, exhibit the non-physical oscillations in the numerical solution, and that is due to instability of the solution. So that condition is very important. It ensures that convection term do not dominate the diffusion term. Now, a difference scheme is said to converge at a point xi if limit h approaches to 0 and tending to infinity. Basically, h equal to b minus a upon n. As n tending to infinity, h definitely will be approaches to 0. Mod ui minus uxi equal to 0. In the classical convergence theory framework for finite difference scheme for the linear boundary value problem, consistency plus stability implies the convergence. So in this above framework, constructed central finite difference scheme is convergent with the order of convergence 2. Now for the same problem, we will discuss an upwind finite difference scheme. So an upwind finite difference scheme for the boundary value problem is defined by equation number 15. Here, second order derivative term is replaced by this central difference operator, while convection term, that term u prime is approximated by the forward finite difference approximation ui plus 1 minus ui upon h. And note that whether we use forward difference operator or backward difference operator, it depends upon the coefficient pi. If function px is positive, then you need to use the forward finite difference operator, and if function convection coefficient px is negative, in that case if convection speed is negative, in that case you need to use the backward difference operator, that is ui minus 1 upon h if pi is negative. So we already taken that pi is positive, px is positive, so that's why pi is positive. So we are taking the forward finite difference approximation for the first order derivative term. So this yields the following system of n plus 1 linear algebraic equations in the n plus 1 unknowns, where ai are the diagonal entries, bi are the upper subdiagonal entries, and ci are the lower subdiagonal entries. So note that pi is positive and qi is negative. So ai with this, if pi is positive and qi is negative, So AI is negative, BI is already positive, and CI is also positive if PI is positive. So, and also you can notice that AI plus BI plus CI is less than 0. So, system correspond to upwind finite difference scheme satisfy the M matrix criteria. So, while central finite difference scheme was conditionally stable, that is that condition, that restrictions you required upon the mass width h by 2 mod pi should be less than 1. Here upwind finite difference scheme is unconditionally stable, but disadvantage with upwind finite difference scheme is that it has a lower order accuracy. It is only first order accurate, while central finite difference scheme is second order accurate but was conditionally stable. So, like we did in the central finite difference scheme, ultimately we lead to this system of linear equations where coefficient matrix A is given by this, U equal to this, and F equal to this. The upwind finite difference scheme is consistent as the local discretization error. Discretization error in the upwind finite difference scheme is this. So you can notice that because of this term, upwind finite difference scheme is accurate only of order of h. This is order of h. And from the sign pattern of the entries on the coefficient matrix A, it is clear that negative of A has the non-positive of diagonal entries, positive diagonal entries, and is irreducible diagonally dominant, thus satisfy the M matrix criterion, which imply that M upwind discretization is stable. Hence, upwind scheme is unconditionally stable but has order of convergence 1. Now note that uh, we can enhance the order of accuracy of upwind finite difference scheme by using the Richardson extrapolation technique. Upwind finite difference scheme is accurate only of first order. Upwind finite difference scheme converges with first order accuracy only. So there are other many other techniques to enhance the accuracy of lower order schemes. You may we have deferred correction approach. We have Richardson extrapolation approach. So here in this lecture, I am discussing only the Richardson extrapolation approach. So in Richardson extrapolation approach, we find two solutions with the same scheme using different step size of h and h by 2. In our case, we apply upwind finite difference scheme to get two different solutions with different step size h and h by 2. So let UIH denote the finite difference solution UI at the point xi, which is obtained with the step size h, and so that UAI plus h minus UIH. UAI plus h is the exact solution and UIH is the approximate solution which you obtained with the finite upwind finite difference scheme. And we know that upwind finite difference scheme is accurate of order 1, that is having accuracy of order of h. So with that, UAI plus h minus UIH is equal to CH plus order of h square, where C is a constant related to the term in the truncation error. Now suppose U2I is another solution with step size h by 2. Note that U2I h by 2 is the upwind difference solution at the point A plus 2I into h by 2. That is again UAI plus h. Basically what you are having, suppose this is the x naught, x1, x3, x4. You find, and mass width is h. You first find the UIH on this mass width. Now we bisect each interval by introducing more points, say x00, x20 and x30. Now mass width is h by 2. Now x2 here a plus ih, and in terms of new mass width, x2 is equal to a plus 2 into h by 2. So u2ih by 2 is equal uih. But here mass width is h by 2. So uai plus h minus u2ih by 2 will be equal to c into h by 2 plus order of h square by the order of accuracy of infinite difference scheme. Now we subtract these two error equations to eliminate the exact solution. Exact solution is uai plus h. So if we subtract second equation from first equation, we are getting ch minus ch by 2. We are getting ch by 2, ch by 2 equal to u2ih by 2 minus uih plus order of h square. That is ch is equal to this term. Now using this result in this equation, using this result, we estimate the error in the final mass solution. So uai plus h minus u2ih by 2 is equal to 1 by 2 into ch equal to this one. So 1 by 2 into 2, that will be cancel out. So ch by 2 will replace by this term u2ih by 2 minus uih plus order of h square. Am I right? So with the help of this estimate, if we construct a new solution, if we consider a new solution ui hat equal to u2ih by 2 plus u2ih by 2 plus this, that is equal to 2uih by 2 minus uih. Then because of this equation, this new solution ui hat will be of second order accurate. Will be of second order because of this, it will be second order accurate. So basically, idea in Richardson extrapolation for affine finite difference scheme is that first find the affine finite difference scheme solution with the mass width h, then find the affine finite difference scheme solution with the mass width h by 2, then take the linear combination of them in this way 2uih by 2 minus uih and consider it ui hat. Now this new solution ui hat will be of second order accurate. So in the same manner, we can construct Richardson extrapolation scheme for the central difference scheme to get accuracy of order of h to the power 4. Since central difference scheme is accurate of second order, so in that case, error equation will have this form. uai plus h is the exact solution at the point a plus is, that is at the point xi. uih is the solution, central difference scheme solution with mass width h, and since central difference scheme is accurate of order 2, so error dependence will have this form uai plus h minus uih is equal to ch square plus order of h to the power 4. Further, if you find u2ih by 2 solution, again it is a central difference scheme solution but with the mass width h by 2. So this point I and 2i will coincide because I with the mass width h, and 2i with the mass width h by 2. So a plus ih will be equal to, in that case, a plus 2i into h by 2. So u2ih by 2 and uih are the central difference solution at the same point but with width h and h by 2 respectively. So since width is h by 2 here, so it will take that form, c into square of h by 2 plus order of h to the power 4. Now we subtract second equation from first equation to eliminate this exact solution uai plus h, and we are getting this equation ch square is equal to 4 by 3 u2ih by 2 minus uih plus order of h to the power 4. Ch square minus ch square by 4, that is 3 by 4 ch square. So this we are getting over here 3 by 4 ch square is equal to 3 by 4 ch square is equal to u2ih by 2 minus uih plus order of h to the power 4. So using this result in this second equation, we are getting ui plus h minus u2ih by 2 is equal to 1 by 4 into 4 by 3. So 1 by 4 will be cancelled out. So C h square by 4 value will be this u2ih by 2 minus uih upon 3 plus order of h to the power 4. So that implies if we consider an approximate solution which we are denoting by ui hat is equal to u2ih by 2 plus u2ih by 2 minus uih upon 3, that is equal to 1 by 3 for u2ih by 2 minus uih. So that approximation ui hat will be accurate with order of h to the power 4. So here linear combination of two solutions we are taking as 4 by 3 u2ih by 2 minus 1 by 3 uih. So this is the linear combination for the central difference approximation if you are applying the Richardson extrapolation technique. Now we know that if u is the continuous solution and uh is the numerical approximation of u, where uh is defined on the mass with mass spacing h equal to b minus a upon n, then numerical method is said to be of order p if it is satisfy this equation in some norm uh minus u less than equal to c h to the power p, where c is independent of mass width h. So we say that convergence rate of the method is h to the power p. So that error generally satisfy this equation uh minus u is equal to c h to the power p plus order of h to the power p plus 1. Now question is that while we are solving a given problem and by any finite difference scheme, then how we can calculate the numerical order of convergence? So there are two cases if exact solution is known to us and if we don't know the exact solution. So if we know the exact solution, in that case, we consider this ratio uh minus u upon by 2 minus u. So uh minus u by this error relationship is equal to c h to the power p plus order of h to the power p plus 1, and by 2 minus u is equal to ch by 2 to the power p plus order of h to the power p plus 1. So simplifying it, it is equivalent to 2 to the power p because c h to the power p will be cancelled out plus order of h. Now taking the logarithm of both sides with base 2, we will get logarithm of 2 absolute value of uh minus u upon uh by 2 minus u is equal to p plus order of h. Here p is the order of numerical order of convergence of the given scheme. If your scheme is accurate of order p, then using this formula for your numerical solution you can get this value. If you are not getting this value, so it means that there is some problem in your code. Now basically if we know analytical solution, then there is no need to go for the numerical methods. So in most of the cases we don't know the analytical solution for the given continuous problem. So in that case, if u is not known to us, we follow this procedure. We consider this ratio uh minus by 2. Uh is the numerical solution with mass width h. UH by 2 is the numerical solution with mass width h by 2, and UH by 4 is the numerical solution with mass width h by 4. So we consider this ratio. So UH minus UH by 2, we can write UH minus U plus U minus UH by 2. So again, uh, we can get this kind of relationship here in this ratio as well. So UH, so there is no harm if we add U and subtract UH. So it will be like this: UH minus U plus U minus UH by 2. So UH minus U gives you CH to the power P plus order of S to the power P plus 1, plus UH minus U gives you CH by 2 the power P. So ultimately you are getting this equation: CH to the power P minus C into H by 2 the power P plus order of S to the power P plus 1, and same in the denominator term: CH by 2 the power P minus CH by 4 to the power P plus order of S to the power P plus 1, which will be equal to 1 minus 2 to the power minus 2p plus order of h, because c s to the power p will be cancelled out, and from here you are getting 2 to the power minus p, and from here you are getting 4 to the power minus p, which is equal to 2 to the power minus 2p plus order of h. Again, after simplifying, it is equivalent to 2 to the power p plus order of h. So again, taking the logarithm of both sides with base 2, we are getting this formula to calculate the numerical order of convergence if your exact solution is unknown. So to verify our theoretical finding numerically, we consider these two test problem. First test problem is this. We consider a simple 2-point boundary value problem where convection coefficient is 1 plus x. So you can notice that 1 plus x is positive, and uh, this show plus x ux, it should be, I think, negative. I will correct it: minus x ux. So u0 equal to 0, u1 equal to 1 minus 1 upon e. So exact solution for this boundary value problem is this: ux equal to 1 minus e to the power minus x. So while you are applying upper bound operator, so your finite difference scheme will take this form: delta square ui plus pi d plus ui plus qi ui equal to ri. And while you are applying central difference operator, your scheme will take that form where uh, d plus is the forward difference operator, d minus is the backward difference operator, d naught is the central difference operator for the first order derivative, and delta square vi is this central difference operator for the second order derivative. And pointwise error we can calculate at each point by using this formula: ein is equal to mod of uxi minus uhxi, I equal to 1 to n, where superscript n denote the number of mesh points used. Maximum pointwise error we find out by using this formula over the whole domain, and then order of convergence we find out by using this formula, that is logarithm of 2 en upon e2n. En uxi minus uhi e2n. If number of mesh points is 2n, it means that mesh width will be h by 2. If mesh width is h, number of mesh points is n. If we double the mesh points on uniform mesh, so mesh width will be h by 2. So that formula will take that form: e log en upon e2n. So you one can notice that with central difference scheme, if we begin with the mass points n equal to 16, then n equal to 32, n equal to 64, n equal to 128. Central difference scheme with n equal to 16 is gives the error of order of 10 to the power minus 5. With n equal to 32 is also error of order 10 to the power minus 5, but roughly half the error correspond to n equal to 16. So that numerical order of convergence we find out below. So you can notice that central difference scheme is second order accurate, and we verify it numerically. We exactly getting the numerical order of convergence to over here. While we are applying Richardson extrapolation with central difference scheme, so we can get that with n equal to 128, error is of order of 10 to the power minus 12, and this is the numerical order of convergence which verify over theoretical finding with Richardson extrapolation. Central difference scheme is fourth order accurate, and we are getting this numerical order of convergence over here, which is approximately equal to 4. Now, for the same problem, we apply the upwind finite difference scheme. So with simple upwind scheme, we already shown that it is accurate of order of h, that is first order accurate. So one can notice that numerical order of convergence we are getting also 1. And while apply Richardson extrapolation, we are getting numerical order of convergence is almost equal to 2. So which is also verify over theoretical error estimates for the Richardson extrapolation with upwind finite difference scheme. So this is the numerical solution profile for this example. Now second test problem we are considering as a turning point problem. Here you can notice that this convection coefficient Px changing its sign interior to the domain at the point x equal to 0 0.5. For x, if point x is less than 0 0.5, so 2 x minus 1 is negative, am I right? And minus 2 is negative, so this 2 into 2x minus 1 is negative. And if x is greater than 0 0.5, this term is positive. So it means that convection coefficient changing its sign, so it is a turning point problem. It's a turning point problem, and reaction coefficient qx equal to minus 4, that is negative. So in that case, exact solution is given by this function. So here again, same manner, our discrete scheme will take this form, but here note that since convection coefficient changing its sign, so instead of d plus, we are taking the difference operator d plus minus, where we use d plus if pi is positive, and we use d minus, that is backward difference, if pi is negative. So here upwind finite difference scheme will take that form. So pi d plus ui if pi is positive, and pi d minus if pi is less than 0. So I already discussed that uses of approximation of first order derivative in this depend upon the of convection term depend upon the convection speed. If convection speed is positive, we will use forward difference approximation. If convection speed is negative, we will use backward difference operator. So it's required to maintain the domain of dependency of difference scheme lie in the domain of dependency of the continuous problem. So that required for that. So for this problem, again, you can notice that central difference scheme is second order accurate, and while we apply central difference scheme with Richardson extrapolation, order of accuracy is 4. And for upwind scheme, we are getting first order accuracy again. And since convection coefficient is changing its sign, so upwind scheme we are using according to this. And upwind scheme with Richardson extrapolation is again we are showing second order accurate numerically also. This is the solution profile. These are some references which I used to prepare this lecture. Okay, thank you. Any question? Dear participants, any question from your side? So note that stability analysis play a very important role in the study of finite difference scheme. So we have to be very careful while we analyze any finite difference scheme for the stability. So that's why instead of initially I taking the coefficient px is positive and qi is less than 0, and later on I shown that why this condition I we required. Yes, I am reading your comment. So if you have any doubt, any query, please let me know. Satyendra, you have written not half but 2000 less in Richardson. What does it mean? I could not get your point. Yeah, uh, because of some amount of error may introduce to the round of error. So numerically, if it is almost, if you are getting three numerically order of convergence, if you are getting 3.99 or 3.8, so it means that you are verifying numerically theoretical order of convergence, because central difference scheme with Richardson extrapolation is accurate of order of h to the power 4, that is fourth order accurate. So numerically we also shown that for initial term that it is exactly of order of s to the power 4, but while we are increasing number of mass points, 128 and up to 128, so you are getting error is of order of h 10 to the power of minus 12, which is very large, very small. So due to finite precision in system, so you may lack some amount of order of convergence there, because there it is around arriving about 3.5. Okay, let me, which slides you are talking? This one, Satyendra? Okay, so here you can notice that with n equal to 64 it is around 3.96, and error is of order of 10 to the power minus 12, with just mass number of mass points n equal to 128. So here it's a little dip in the numerical order of convergence. Over here it is from 4, so that is due to, because of due to amounting of round of error due to finite precision system, because this number is very small, 6.0013 into 10 to the power minus 12, that is due to that. Okay, so with this I conclude today's session. So if you find any doubt, any query, you may email me to discuss this. And tomorrow I will discuss about stability and consistency for the finite difference scheme for partial differential equation. Okay, thank you.
Thank you, Dr. Professor Vikas, for a very informative and nice lecture. And as you have already told to participants, if they have any query, they can write to you on your email, so that you can see the query and you can respond them accordingly. Somebody is writing, will be any simulation code based on this theory? Will there be any simulation code based on this theory?
Okay, I will share those simulation code based on this theory. I will share.
Yes, yes, yes.
I
And
will share the code for the upwind scheme as well as central finite difference scheme and with Richardson extrapolation technique.
uh, yes, thank you, Professor Vikas. One request: you can share the PDF file of your PPTs to us so that we can upload them on the Canvas platform.
Okay, after correcting few typo error, I will share it with you, Professor Rahul.
Yes,
Because
yes, yes.
I found that there are some typo errors, so I will first correct them and will share with you.
Yes, yes, sure, sure. And I requested earlier in the morning session to Professor Ashish Avasti also to share the PDF file of his slides. And yesterday also he delivered one lecture, but I'm not sure whether he has sent the PDF file of his slides. So if possible, can you please get the PDF files of his slides also?
Okay, okay, fine.
So we can upload both together at the Canvas platform. So with this, I conclude this session and hope all the participants have gained the knowledge about the topics which the speakers of today's session in the morning and afternoon session what they have covered. Uh, Tomorrow again we will be meeting around 10, and on Sunday we have one lecture